All right, so welcome back to the lecture 9. Today we are going to sort of cover this lecture in the third part, where I'm going to talk about what are called as Monte Carlo simulations. Monte Carlo simulations are a popular tool for attaining numerical solutions for problems that might otherwise have analytical solutions. And we are going to cover this topic on Monte Carlo simulations for specifically assessing statistical inference under spatial dependence. So that would mean that I'm going to sort of specify or talk about a computational algorithm or an experiment design that can be implemented on a personal computer, which can provide us, the results that we have derived in the previous lecture for statistical inference under spatial autocorrelation or a given spatial dependence structure. All right. So a little bit introduction on Monte Carlo simulations. So Monte Carlo algorithms or Monte Carlo experiments are computational algorithms that employ randomness and repeated sampling to arrive at numerical solutions. So critically, I am pointing out that Monte Carlo simulations will exploit stochasticity, right? So they will exploit randomness in terms of designing an experiment, and they will then also rely on repeated sampling, right? So you are going to be somehow sampling again and again from a from a parent distribution, okay? And the example that we covered in the last lecture, that is of a circular city, we can establish whether or not the mean estimator and the confidence bounds, the 95% confidence bound, are indeed consistent estimators in the presence of spatial dependence using simulations, right? So that's the sort of power here. And these methods provide an alternative for the analytical framework that yields a deterministic solution, right? So there, we had when we said that, the mean of prices on a circular city are n plus 1 over 2, we did not say that they could be n plus 1 over 2 plus minus something, right? So we kind of had a analytical solution that the mean of prices for the circular city is n plus 1 over 2, where n is simply the number of homes in this city, right? So let's begin looking at the steps in Monte Carlo simulations. Before we do that, I just want to sort of give you a very quick recap of this practice problem that we have worked with, where we introduced the circular city and we solved for the mean estimator, the variance estimator, the standard deviation estimator, and the 95% confidence bounds for home prices, spatially distributed on a circle with a circumference of k units. Okay, so here, if you just a quick reminder, we were basically working with first order neighbors on a circle. So we had entities P1, P2, P3, P4, which are denoting both prices as well as location. So the index on the price P is the location. So location 1, location 2, location 3, and corresponding price P1, corresponding price P2, P3 respectively on these locations all the way till location N. All right, and we are given a specific spatial dependence structure. We talked about this in detail. You can refer to the previous lecture on details of what this means. And for this particular scenario, we estimated, population mean. What would be the best guess of population mean? We said it will be P bar. We came up with a analytical solution of P bar, that is n plus 1 over 2. We came up with analytical solution of variance of P bar, which was sigma squared over n times 1 plus 2 lambda. Again, all of this was done step by step in detail in the previous lecture. And then we had the estimator for standard deviation of P bar, and then we had the confidence bounds, right? So now today's lecture, in this lecture, we are going to try and arrive at these estimators using simulations rather than mathematical derivation or analytical derivation. So we are going to arrive at them numerically is what the agenda of this lecture is. Okay, so let's go over the steps in Monte Carlo simulations and through this also learn what are Monte Carlo simulations. So step 1, it says start with a true model that employs a stochastic component to specify the given spatial dependence structure. So first of all, we say start with a true model. True model of what? Of the price process on this circular city, right? So true model for PIs, right? For each PI, we need a model that helps me arrive at this value of PI. This model should employ a stochastic component, right? So there will be some kind of a random number which will be used, or random variable that will be used to specify PI. So we can sort of, say that, let's say it is UI with, PDF f of u, right? So when we say stochastic component, basically means a random variable, right? And I am just, specifying it to be UI. And then it is supposed to be able to explain or encapsulate the given spatial dependence structure. So when I say the given spatial dependence structure, what I am talking about is that prices for first order neighbors are correlated. Okay, and the degree of correlation was specified with this parameter lambda, right? So we need to parameter lambda, right? So this is the variance covariance matrix or the correlation PI PJ structure that was specified in the practice problem earlier. Okay, so let's try to do that. Okay, so we are going to say, let PI equals I plus UI. Now I is simply the index which is specifying the location as well as giving it a deterministic value. So I by itself is the systemic or deterministic component of price. What do we mean by deterministic component? What it really means is that if I'm standing at location 1, I know that level of price that I'm looking at will be closer to 1 plus a random variable, right? And if I'm standing at location 10, then I have an index of what level of price I'm looking at. If I'm standing at location 100, a location 1000, I am giving a deterministic level to prices through this systemic component I. And then to this systemic component, I'm then adding this random component, random or stochastic component of price, right? And now the final condition for this stochastic component is that it should specify a given spatial dependence structure, right? So we are going to write UI as lambda over 2 epsilon I minus 1 plus lambda over 2 epsilon I plus 1 plus epsilon I, such that epsilon i's are IID, so independently and identically distributed with according to a normal distribution with mean 0 and variance 1. So epsilon i's are basically IID random variables which behave according to a standard normal distribution. Okay, and now we have to check, we should validate or check that this indeed specifies the given spatial dependence structure, right? So our true model is all these equations combined, right? So we have pi equals I plus ui, where ui equals lambda over 2 times epsilon I minus 1 plus lambda over 2 epsilon I plus 1 plus epsilon I, right? So intuitively you can see that I'm using these epsilon i's to sort of specify spatial dependence. So the error component or the stochastic component at location I depends on the error component at location I minus 1 and on the error component at location I plus 1, right? So I'm bringing in the spatial dependence through the stochastic term. But I need to now make sure or validate that this given structure is indeed enough or sufficient for me to ensure that it follows first order correlation, with the degree of correlation being given by parameter lambda. To do that, I'm going to sort of say check that covariance of pi and pi plus 1 should equal lambda, and covariance of pi and pi minus 1 should also equal lambda, right? So let's do that. Okay, so covariance of pi and pi plus 1, I'm going to expand this. I'm going to say covariance. So pi equals I plus lambda by 2 epsilon I minus 1 plus lambda over 2 epsilon I plus 1 plus epsilon I comma and then pi plus 1 is I plus 1 plus lambda over 2 epsilon I plus lambda over 2 epsilon I plus 2 plus epsilon I plus 1. Okay. Now, I and I plus 1 are deterministic components. So if I look at a deterministic component and think about the covariance of this deterministic component with all the other, deterministic and random components, they are going to be 0, right? The covariance of epsilon I minus 1 with I plus 1 is 0. Epsilon I, it's going to be 0 because remember, epsilon i's are IID, right? So they are independently, I minus 1s are independently distributed of i's, right? Epsilon i's, right? So this covariance is going to be 0. With epsilon I plus 2 is going to be 0, and then epsilon I plus 1, this is again going to be 0, right? So there is no contribution to the covariance of pi and pi plus 1 from either the deterministic term I or this spatially lagged epsilon I minus 1 term. Now let's come to the epsilon I plus 1 term. So I'm going to look at epsilon I plus 1. It's going to have no correlation or no covariance with the deterministic. It's deterministic. They can't co-vary because the deterministic component does not vary at all, right? And then I plus 1 with epsilon I, the covariance will be 0 again because I plus 1 is independent of epsilon I. Second, I plus 1 with I plus 2 is again going to be 0 because they are IID. Finally, you have I plus 1 and I plus 1. So I found my first, component of covariance that is indeed going to sort of contribute to the covariance of pi and pi plus 1. So that is covariance of lambda epsilon I lambda over 2 I plus 1 I plus 1. Now I'm going to come to the last term, which is epsilon I. So epsilon I with the deterministic component has 0 contribution to the covariance. Epsilon I and epsilon I, yes, we will have a covariance contribution, right? So we can write covariance lambda over 2 epsilon I comma epsilon I. And then with epsilon I plus 2, I have 0 contribution because they are IID, and with epsilon I plus 1, again 0 contribution because they are IID. Now, if we come back to this right hand side, we have covariance of lambda over 2 with epsilon I plus 1 and epsilon I plus 1. So this here I can bring out this lambda over 2, which is a constant. It will just come out, and I will have covariance epsilon I plus 1 comma epsilon I plus 1, which is nothing but variance epsilon I plus 1, and similarly you will have lambda over 2 variance epsilon I. Now looking at the fact that the variance of epsilon i's is simply 1 for all I. So we have the covariance between pi and pi plus 1 will simply sum to lambda. Similarly, you can show, and you should at your time show that covariance of pi comma pi minus 1 will also be equal to lambda. So indeed, what's going on now, what's happening now is that we have a true model. We have a true model of home prices that exhibit the spatial dependence structure on a circular city, right? So this spatial dependence structure is the given spatial dependence structure, right? We should be able to sort of follow or specify the structure that we are working with, right? So we are indeed able to work with, so thumbs up to step 1. Okay, so let's move on to step 2. Now it says draw random components of the size of the circular city, that is n. Okay, so for this example I'm simply going to say n equals 100. So what I'm saying is that there are 100 homes located on this circular city, right? For the purpose of understanding, there are 100 homes located on the city. So this is P1, P2, P3, P4, P5, P6, P7, P8, keep going till P100, and just before P100 we'll have P99. Okay. It says draw the random components of the size of the circular city. That means I have to go back to my model that I have specified earlier. So I'm going to do that. I'm going to write down the model at the top of your slide here. So I have Pi equals I plus Ui, where Ui equals epsilon I plus lambda over 2 epsilon I minus 1, lambda over 2 epsilon I plus 1, such that epsilon i's are simply IID normal 0, 1 for every I. Okay, so what am I doing now? Okay, so now what I'm doing is I am generating or constructing my own data. I'm simulating a data set of prices of these 100 homes located on the given circular city. What that would mean is that I can just go to an Excel sheet, right, and start populating it as follows. So I have my rows, okay, I have my rows. The first row is I, that is the ID, the home ID. I have first, second, third, fourth, fifth, sixth, keep going, 99, 100. Okay, then I have epsilon I minus 1, epsilon I, and epsilon I plus 1. Each of epsilon i's, that is epsilon I minus 1, epsilon I, and epsilon I plus 1, they are simply normally distributed with 0 mean and variance 1. So I can simply apply a random draw from a standard normal distribution in an Excel sheet, which is a coded exercise. Right? It's already canned in the Excel sheet, so you can go ahead and do that. But what you're going to expect is you're going to have these 0.01, 0.03 minus 0.9, and so on and so forth. So you're going to have these random entities generated individually one by one, so that there is no relationship between epsilon I minus 1, epsilon I, and epsilon I plus 1. You are simply drawing from a standard normal distribution 3 times, right? The first time is, you are doing it for epsilon I minus 1. The second time you're doing it for epsilon I, and third time you're going to do it for epsilon I plus 1, right? So let's say I get a minus 0.23 here as the first row, then I have 0.56, and I have 0.8, and so on and so forth till 100 values. Let's say here I have 0.9, 0.8, 0.7, and so on and so forth. Right? So there are random entities being generated. Of course, when you will take mean of any of these random entities, they will turn out to be 0 because you're drawing from that distribution, right? Or very, very close to 0. Right? That's what we should expect. Finally, once you have done that, you have created data, so basically you have 4 columns that you have generated. So first one is a deterministic column. It is simply the value of the ID itself, right? So it's just a deterministic. When I say I equals 1, I don't mean I is 1 and plus minus something. I mean I equals 1. It's deterministic, right? And then I have 3 different normally distributed independent random variables being drawn, which I denote to be epsilon I minus 1, epsilon I, and epsilon I plus 1. Okay. Of course, when I is 1, epsilon I minus 1 means 100. Yeah, I'm looking at the 100th home, and epsilon I plus 1 means that I'm looking at the second home, assuming I'm going clockwise on the circle. So using these, I can then define Pi as I plus lambda over 2, right? Epsilon I minus 1 plus lambda over 2, epsilon I plus 1 plus epsilon I. Okay. Now, in order to populate Pi, the column of Pi, data in the column of Pi, I must also specify lambda. Okay. So in the true model, I'll go back to my true model, and I'm going to specify, I'm going to say let lambda equals 0.4 for the Monte Carlo simulations. Okay, and then once I have my the specification, I am basically saying lambda by 2 is 0.2, and I have data on these values. So Pi is nothing but 1 minus 0.2 multiplied by minus 0.01 plus 0.2 multiplied by 0.9 plus minus 0.23, which will turn out to be some numerical value, right? So you have created this data set of PIs. Okay, so you have simulated, these are simulated data for PIs. The beauty of these data are that they follow the exact same first order spatial autocorrelation structure that the practice problem provided us in the previous lecture, right? So now we have actual values to work with that behave according to the analytical problem that we were solving in the previous lecture. Step 3, so evaluate PIs along with mean value, its mean value, variance, standard deviation, 5th and 95th percentiles. So we have already in step 2, we collected this data on PIs. So now I have I, which goes from 1, 2, 3, 4, 5, 6 all the way to 99 and 100. I will also have these values of PIs which I have created in step 2. So I've constructed data on P1, P2, P3, P4, P5, P6, so on and so forth till P99 and P100. Once I have these data, once I have the data, I can calculate the mean, which is simple. So I can just say P bar equals summation I equals 1 to 100 Pi. Remember, this P bar is a function of lambda being set as 0.4. It is also a function of n being set as 100, right? So it's for 100 homes. You could be working with 1000 homes. You could set n equals 1000. It's not going to be a very difficult exercise to do that, right? You can see that, right? So what I am saying is that my Pi itself is a function of setting lambda equals 0.4 and n equals 100, and this is what it will look like. Similarly, I have, sorry, it's not Pi, it's P bar. Similarly, I have variance of Pi, variance of, Pi or P bar, that will, variance of Pi will be summation I equals 1 to n, which is 100, Pi minus P bar, the whole square divided by n minus 1, which is 99, right? Now this I can call as sigma hat squared P. With that, we know variance of P bar will be just sigma hat squared P divided by n, that is 100, right? Standard deviation of P bar will be sigma hat squared P by 100, the square root. And the 95th confidence bound is nothing but that I order these data, order PIs in descending, right, in descending values. So basically you have the highest value as the first topmost value, and then it just keeps going down to the minimum value. So descending from max of Pi to min of Pi, and then you pick from bottom you pick the fifth value. The fifth value from min Pi will be the 95th percentile of the prices, and the 95th value from bottom, that is the minima of Pi, will be denoted as so I made a typing error here. So the top one will be P5, the 5th percentile, and this will be 95th percentile. And the confidence bound for PIs will be P5th to P95th. All right, so this is a simulated mean, a simulated variance, a simulated standard deviation, and a simulated bound, right? That is very, very important. Okay, this is for Pi. If you wanted the confidence bound for P bar, you could sort of, we'll see how to do that now next. So step 4 is replicate steps 2 and 3 500 times. So now we are going to replicate the simulated prices and their averages. Okay, so let's see. So step 2 was that we first construct data on Pi. Step 3 was we collect these statistics on Pi. Okay, and then finally we create these replicas of Pi, right? So we basically have the first time we did that, we can say that was replica 1. For that replica we got P bar m, right? We got variance of P bar m equals 1, sorry, so at P bar m equals 1. The standard deviation of P bar for m equals 1. Okay, so we got these values. And then, you know, we can create the second replica. The second replica will be, we start the process all over again. We have our i's, we draw, you know, we create these random draws for epsilon I minus 1, for epsilon I plus 1, again construct data on pi's, and then get our p bar, right? So I'm going to get p bar for the second replica, for the third replica. Remember, in each replica, n is fixed at constant 100 and lambda is kept at 0.4. So we don't change those parameters. All the p bars are simply because we are drawing from the normal distribution with 0 mean and variance 1 for the second time, for the third time, for the fourth time, and we keep doing it 500 times, right? So we are going to keep doing it for 500 times and we are going to collect our data, right? So we are going to store these p bars for till m equals 500. Sorry about that. Right, so we have these replicas of p bar going from the first replication, the first replica to the 500th replica. The only very, very important thing to keep in mind is that for all these replications, right, so throughout all these replications, we fix n equals 100 and lambda equals 0.4. Okay, so this is step 4. Let's go to step 5. The step 5 says contrast the numerical estimators with their analytical counterparts. So now we have, you know, the numerical estimators in the sense that if we go back, we have p bars, which we have 500 values of p bars, right? So we have an Excel column of m's, which goes from 1 to 500, and then we have p bars, which, you know, go from which are different values of average prices through each iteration of simulated construction of mean. Once I have 500 means, I can take a meta mean or some kind of a p bar, which is nothing but summation m equals 1 to 500 p bar m over 500. Right, so I can get my p double bar. Similarly, I can get my variance of p bar as nothing but summation m equals 1 to 500 p bar minus p double bar the whole squared divided by n minus 1, which is here, which will be m minus 1 here, which is 500 minus 1, that is 499. Right? Standard deviation of p bar is basically the square root of the variance of p bar calculated just now. And the 95th and the 5th percentile will nothing but, I will simply take these values that I have generated from 500 replicas. I'm going to order them from the smallest value or to the largest value, or the other way around, from the largest to the smallest. Let's work with from the smallest value to the largest value, right? The value that I'm looking at, which is at the 95th percentile, is the 25th value, starting from the smallest value all the way up to the 25th value that I find will give me p bar 5th percentile, right? And 475th value, starting from the minima all the way up to the maximum, 475th value in this simulation will be my p bar 95th. Okay. Now realize that these estimators, the p double bar, variance of p bar, standard deviation of p bar, and the 5th and the 95th percentiles are nothing but, they are really numerical solutions of, the mean estimator for, prices that are spatially autocorrelated, and all other statistics, the second moment, as well as the 5th percentile and the 95th percentile, right? So these percentiles are simulated confidence bounds for p bar, right? So as a next step, what we are going to do is we are going to contrast them. We can then contrast them with the analytical solutions that we spent a full lecture previously to arrive at, right? For example, now I have my numerical solution. I have my numerical solution where P double bar is nothing but summation m equals 1 to 500 P bar indexed with replication m divided by 500 against the analytical solution where I calculated this P bar to be n plus 1 over 2. N being 100, I basically have 101 over 2. So I can contrast whether or not they are close, and if you conduct this exercise, you will find that they are going to be indeed very, very close, right? And which makes sense. But one thing that we have to understand is that for both these cases, n is fixed at 100 and lambda at 0.4. Okay. Similarly, the variance in case of the simulated solution, variance of P bar is summation m equals 1 to 100 P bar m minus P double bar whole squared divided by 499, right? And in the other case, it was P bar equals sigma squared by n 1 plus 2 lambda. Remember, sigma squared in our case has been fixed to we'll have to figure out the variance of P, which will be variance of Pi from where Pi equals I plus Ui. Remember, Ui is a function of 3 epsilon I, right, which is I plus epsilon I by 2 into lambda I minus 1 plus epsilon I plus 1 into lambda over 2 plus epsilon I. So the variance of Pi, which I'm going to just quickly calculate here, is going to be lambda squared over 4 plus lambda squared over 4 plus 1, which is nothing but 1 plus lambda squared over 2. So variance of Pi is 1 plus lambda squared over 2. Lambda is 0.4, right? So lambda squared is going to be 0.0016, right? So 1 plus 0.0016 divided by 2, which is nothing but 0.0008. So this is 1.0008, right? So I'm going to now change this to my analytical solution will be 1.0008. You guys should definitely check my calculations. Divided by 100, 1 plus twice of 0.4. So in black, we have an analytical solution. In green, we have a simulated solution, right? They should be very close, right? If our simulations are correct, they're going to be very, very close, right? Then, I can sort of do the same thing for, the standard deviation of P bar and the standard deviation of, P bar, which is nothing but variance of P bar from the analytical solution. And then finally, my confidence bounds, are P fifth, P bar fifth, and P bar 95th that we calculated previously, right? We calculated on the previous slide, right? And in the analytical case, this was given by so the confidence bounds. Just a second. The confidence bounds were given by n plus 1 over 2 minus 1.96 into sigma over root n 1 plus 2 lambda to the square root, comma n plus 1 over 2 plus 1.96 sigma over root n 1 plus 2 lambda square root, right? So these were my confidence bounds, and they should match the ones on the left hand side in green. Okay. Finally, we can check for consistency of our estimators. And what does it mean to check for consistency? That would simply mean that as n approaches infinity, practically it would mean as I increase the value of n, the size of the circular city or the number of homes, the density of this city, what I should find is that the simulated mean, variance, standard deviation, confidence bounds should become closer and closer to their analytical counterparts. Okay, so we have really gone through a full-blown simulation exercise to arrive at numerical solutions for estimators of mean, variance, so the first moment, the second moment, the confidence interval, so to conduct statistical inference in case we did not want to go through all that math, right? So we can use computational algorithms, computational simulations to get there. So Monte Carlo simulations are very, very important. They are used widely. So this is a very important topic, and I urge all of you to sort of go over it one more time. And I hope you had fun learning Monte Carlo simulations. See you next time.